All right, thank you, Andreas. It's a great pleasure actually to kick this off, the OWLE Colloquium and Seminar Series. Since this is the first talk, I guess I'm a little bit of a guinea pig. Let's see, I can actually see the chat. So if you post an urgent question in the chat or if you raise your hand, I will try and react, but we'll see how that goes. Otherwise, we'll just discuss everything at the end. So the topic today is the ISO DAR high intensity compact cyclotron. This is part of our proposed experiment, the search for sterile neutrinos. And I will mainly be talking about the design and the simulations. And then at the very end, I have a few slides on our plans to incorporate machine learning into the optimization of our cyclotron design. But this is very new, so bear with me on that. All right, so at the beginning, I will give you a bit of a motivation. I will explain what the ISO DAR experiment does, and we'll go into some of the challenges of providing a very intense proton beam in an underground laboratory environment. Then I will jump right into the cyclotron design and simulations. I will tell you about the building blocks of our system and how we simulate them and what the current status is. And then finally, as I mentioned, I have a few slides on how we are planning on incorporating machine learning into this. The picture on the title slide, you may know it from the OWL webpage, was drawn by Chantal Adelman. Just wanted to give the proper credit here. And with that, let me go right into the neutrino physics. I'll keep it brief because I know we're all accelerator physicists, but it's always nice to know where the technology that we're designing will be applied. And so in the neutrino standard model, there are 3 known flavors. They're part of the lepton-weak doublets. And here on the bottom, you can see a picture of the standard model of particle physics. And here you can see the 3 neutrinos and their respective partners, the electron, muon, and tau. And those interact through the weak force with each other. Now, since a while, we know that neutrinos actually have mass and they oscillate. This was not always known. In the beginning, in the standard model, neutrinos were massless. Now we know that they have a small mass. And there was a very famous experiment at Super K in '98, and then lots of other experiments thereafter that saw neutrino oscillations. And that means when a neutrino is born in a certain flavor eigenstate, it can actually, while it's traveling, change its flavor. So a muon neutrino might become an electron neutrino, and vice versa. So the way that this is explained theoretically is that there are mass eigenstates and flavor eigenstates, and they're not aligned, so they mix. This is described through a mixing matrix. And here on the bottom, you see a plot from the Camland experiment. This was published in 2003, where you can see the survival probability of electron antineutrinos as a function of the ratio of distance traveled to neutrino energy. And what you can see here is a clear oscillation curve or oscillation wiggle, and that demonstrates this mixing. Now, since then, even more interestingly, several experiments have seen anomalies in this oscillation probability. One of them is, for example, the LSND experiment. And here you can see the prediction in red and green, or background and prediction in red and green. And then in black, the data points for short baseline. And in blue, you can see a possible explanation for this excess. And that would be another neutrino that was dubbed sterile neutrino. Because from other experiments, we know that there can only be 3 neutrinos that interact through the weak force, but there could be other neutrinos that do not participate in the oscillations, but not interact through the weak force, and those would then be sterile neutrinos. So this would be on the order of 1 eV² mass splitting to the other neutrinos that we know of, and it could be an explanation for these anomalies. The problem is that there are many different experiments that see anomalies, and those anomalies are not always the same. And so there's a lot of tension in the sterile neutrino hypothesis. Antineutrinos and neutrinos do not act the same. Appearance and disappearance searches do not quite overlap in their results. And so you can do global fits to all of these experiments, and you can find best fit points, of course, but every time you kind of separate these global fits into these aforementioned, let's say, disappearance and appearance searches, for example, you see tension. And so what we need is a definitive experiment that shows through shape analysis, so something that is independent of some of the systematics that are plaguing other experiments, that whether or not there are sterile neutrinos. And one of these experiments that has been proposed several years ago is IsoDAR, the isotope decay at rest experiment. And we envision this to happen at CAMLand, which is a kiloton scale liquid scintillator detector that is in the Kamioka mine in Japan. So this would be a search for sterile neutrinos through oscillations at short distances. Short distance in this case means that from the neutrino source to the detector, there's about 16 meters distance. And the neutrino energy, as you can see here in this plot, peaks at about 6 MeV. The way that the neutrinos are produced is by shooting a very intense proton beam at 60 MeV into a beryllium target where neutrons are created. These neutrons then capture on a surrounding very pure lithium-7 sleeve. The lithium-7 becomes lithium-8. The lithium-8 almost immediately beta decays and produces a very pure electron antineutrino beam. I mean, beam is maybe not the right word here because this is an isotropic source, but all the electron antineutrinos that make it into the detector can then be registered through inverse beta decay. And we can plot then the observed versus predicted as a function of the distance traveled over energy, like similar to the plot that I showed before from CAMLand. Now here you see just one example with some standard parameters that sterile neutrinos might have. So the mass splitting could be about 1 eV square, and the sine squared 2 theta, that's the mixing angle from this mixing, is one of the parameters in this mixing matrix, could be 0.1. Of course, these are just test values to show what a signal would look like. And you can see that there's a nice oscillation curve that you would see inside the detector. So the beauty of this is that because CAMLand has very good energy and vertex resolution, so we know pretty much exactly where the interaction happens inside the detector, and we know what the energy of the neutrino was. We have a very small uncertainty on the L over E, and we can make a very nice shape analysis to show whether or not there is one sterile neutrino. However, there could also be more than one sterile neutrinos. As I mentioned, there's tension in these models. And so this experiment, the IsoDAR experiment, could actually distinguish between one sterile neutrino, two sterile neutrinos, or even models with a sterile neutrino that decays as it travels. So here is a prediction for a curve with two sterile neutrinos with parameters that were published in this paper. So you can see this is a really nice experiment that would be decisive within 5 years of running, and give us a lot of insight about sterile neutrinos and and whether or not they exist. Here's what neutrino physicists like to show. It's an exclusion plot where you can see here are some of the global fit values. So this is again the mixing angle and the mass splitting. And here are some global fit values from different groups. And then here is the allowed region from something we call the reactor anomaly. This is one of these anomalies that led to the hypothesis of a sterile neutrino. And you can see that with IsoDAR, we would be able to cover all of these values quite nicely. So this would be IsoDAR at CAMLand running for 5 years. Here's an older plot that I like to show because it shows what we see when we actually see something. So these exclusion plots always show what we don't see. So basically it means if we don't see anything, then we know that within here there's nothing. But if we do see something, then it could be a dot in this parameter space surrounded by some contours for how certain we are about finding something or having found something. And so with the 1 sigma and 5 sigma contours, these are possible data points for stellar neutrinos. All right, so how do we produce this 60 MeV proton beam? And this is really the meat of the talk, right? The cyclotron we have determined is the best suited accelerator for this. They have demonstrated very high intensity for compact accelerator system. The state of the art here is, of course, PSI Injector 2 with 2.7 milliamperes of protons coming out. Unfortunately, this is not quite as compact as it can be because it's a separated sector cyclotron. Commercial cyclotrons are typically able to produce about 1 milliampere of protons, and this is also usually using H- as the accelerated particle, and then using stripping extraction to have a very clean extraction from the cyclotron. And they can be very compact. So these are the workhorses of the medical isotope industry, actually. Cyclotrons are also quite well understood. They're fairly cost effective, and as I mentioned, they can be compact. So here in this cartoon picture, you can see our cyclotron as it's connected to with a short beamline to the target. So here in the middle, you have the beryllium, and then surrounding it, you have the lithium-7, and then a lot of shielding, because of course we have to worry about rock activation and disturbing our own experiment. And so shielding is really a very important aspect of the target. Luckily, we at MIT don't have to worry too much about the target. This is something that Columbia University is working on, and we really focus on the cyclotron. This is and this then is the Camelot detector at about 16 meters different. All right, so our cyclotron is a compact isochronous machine running in harmonic 4 at 32.8 megahertz. Isochronous means that we're using strong focusing where we have along the beam path we have regions of high and low magnetic field. This is also shown here for a different cyclotron. So I borrowed this from Tim Koth from his website. Just because it really nicely shows two things. One is that for the vertical focusing, you need this strong gradient between hills and valleys. And then in order to overcome relativistic limitations, you also need the average magnetic field to increase radially outwards. So those are the two staples of the isochronous cyclotron. And then we accelerate the beam using RF cavities. In this case, we have 4 double gap cavities. So at the edges of these golden triangle shaped cavities, the beam is accelerated every time it goes around. So here I'm showing the main building blocks of such a cyclotron. And this is using the example of a 1 MeV test cyclotron that we studied quite extensively a few years back. And the purpose of this study was to see whether or not we can actually produce a very high intensity beam that's not protons, but H2+ molecular hydrogen ions. And I'll explain why in a second. And then how we can inject this through, or whether or not we can inject this through a very large so-called spiral inflector. This is a device that, that creates a spiral shaped electric field by applying high voltage to these two electrodes here, the green and the blue. And in combination with the magnetic field of the cyclotron, this guides the beam through this spiral into the median plane of the cyclotron, where the beam can then be accelerated and guided by the main field, by the main cyclotron magnetic field. So here is a photograph of this test cyclotron, and here you can see 2 of these Ds. So the test cyclotron only had 2. For the full IsoDAR cyclotron, we will use 4. So there will be 2 more on the top and the bottom. And unfortunately, the spiral inflector cannot be seen as it is shielded by a grounded housing here. But this is where the beam comes out, and then every time it crosses a gap, it will be accelerated. And of course, you'll know that during the acceleration process, we can only populate a small window in the RF phase. Otherwise, we lose particles due to them not being in sync with the RF and being, too much or too little accelerated. And then finally, once the beam has reached its design energy, we want to extract it. And in the IsoDAR system, we use an electrostatic septum for extraction. And you can see here again a cartoon of how this works. So here's the main acceleration, if you will, and then you have the n-1 turn, which is accelerated a little bit more to become the nth turn. So there's a little bit of energy gain here. And of course, in order to keep the extraction clean, we want this energy gain to be as high as possible. But when the particles in the nth turn then enter this extraction channel, where we have a very thin septum that is grounded and a puller, I like to call it, electrode that is at the negative high voltage, the particles feel a little force, electrostatic force, pulling them radially outwards. And so instead of going around in another circle, the particles will then move outwards more and more and will reach a region of lower magnetic field where they will then at some point be able to be guided out. So we have these three main components: injection, acceleration, and extraction. Now, what are the challenges? Why can't we just say, okay, commercial cyclotrons do 1 milliamp, we want 10, so let's just inject more beam? Well, the problem is mostly space charge. Space charge, the repulsive force of the positively charged, or in the case of H minus, the negatively charged particles to each other, immediately and always leads to beam growth and potentially to beam loss. So this is a real challenge for high intensity beams, and it's mostly a problem for the low energy part of the accelerator. So right after the ion source in the low energy beam transport line, but also here in the spiral inflector and during the first few turns, the beam tends to grow in vertical and radial direction, and also longitudinal quite strongly. Another challenge is the phase acceptance. If we accelerate protons, we can only populate a very small phase window. Otherwise, we lose the particles that are outside of this phase window. And if that happens, we need to inject more current to compensate, and then we will have more losses. And these losses will lead to undesired effects potentially, multipacting, heating up of parts of the machine, and even damage through sputtering. And also it increases the energy spread, which then immediately leads to problems at extraction, because energy spread means spread in radial direction of the beam size, and that then will lead to more particles terminating on the electrostatic septum, and the septum can only tolerate a certain amount of power. At PSI, it was determined that in order to keep the activation of the septum to a limit where you can still do hands-on maintenance, you want to lose less than 200 watts on the septum. Here's a picture of a simulation of an earlier version of the IsoDAR cyclotron, actually, and you can see you have two neighboring turns here. And this was done with 1 million particles. And you can see that even though the turns are well separated, there's still some particles in between those two turns. And those particles would then go straight into the electrostatic septum here. So overlap of halo is a big problem. It's directly related to energy spread and to space charge in the early turns, and is something that we have to consider very carefully. So how can we do this? What are the building blocks that we can improve and that we can change to mitigate all of these issues? Well, the first one is right at the beginning, the ion source. So what if instead of protons we actually accelerate H2+? H2+ carries 2 protons bound together by 1 electron. So if we accelerate this, and then at the end, after extracting from the cyclotron, we strip away the electron, then we get 2 protons back. So that means we can accelerate half the current and get, so we can accelerate 5 milliamperes of H2+, and then we can strip into 10 milliamperes of protons. Of course, H2 plus is twice as heavy, so that means we need a larger machine, and we need to accelerate to a higher energy overall. So instead of 60 MeV, we need to accelerate to 60 MeV per AMU. But it's not a perfect balance, so we still win a lot by accelerating H2 plus instead of protons in terms of space charge. So this helps with injection, it helps with the LEBT, and there's actually some other exciting way to exploit this, and I'll talk about this in a little bit, keep you in suspense for just a couple of slides more. The other thing that we can do is we can very aggressively pre-bunch the beam to get as much as possible into these 10 to 20 degrees of phase window. And we do this with an RFQ that is directly inserted into the cyclotron. You can see this in this picture here, for example. Here on top, we have the ion source, then we have our very short LEBT, and then we have an RFQ that goes very deep into the cyclotron that pre-bunches the beam, which is then immediately going through the spiral inflector into the median plane. And then we can also use an effect that was first seen at PSI Injector 2, which is called Vortex motion. This is a beam dynamics effect that happens in isochronous cyclotrons, where the combination of space charge and external focusing leads to a kind of a curling up of the beam. And I'll show a number of pictures later. That keeps the beam small and enables much cleaner extraction if the cyclotron is designed for it and if we have matched the beam well in the central region. And then finally, we can protect the septum with a foil, which is this additional exciting way, and I'll show this in a bit. All right, so let's talk a little bit about the ion source first. At MIT, we have built a multi-cusp H2 plus ion source. Multi-cusp ion sources are very robust, sometimes also called bucket ion sources. They are basically you have a number of permanent magnets that are arranged in an alternating way around the ion source body and on the back plate and front plate, and they produce a confining magnetic field. Then you let in some gas. You also have a filament. The filament is heated, emits electrons. These electrons are then accelerated towards the front plate through a potential difference of about 50 to 100 volts. That's enough energy to ionize the H2 gas. And so you create a plasma, a small discharge. Well, actually, it's not that small. So you create a discharge between the filament and the front plate, or the whole source body. And the magnets confine this plasma inside the source, and then H2 plus ions are drifting out of the source here through the extraction hole. And then you have a system of electrostatic electrodes that guide, shape, and slightly accelerate the beam to form, or the particles to form your beam. So here's a photograph of our beam. The nice thing about a high intensity H2 plus or even proton beam is that if your residual gas pressure is fairly high, you can actually nicely see the beam as this purple glow, and you can take photos of it. We usually measure the beam with a Faraday cup right after the source. So we have seen a nice high current density out of this source of 40 milliampere per square centimeter. Unfortunately, we have then determined that this is mostly H3 plus, and so we're now retuning the source to give us a maximum amount of H2 plus. The latest that we have seen is actually about 90% H2 plus, but not at these current densities. So this is still a work in progress, but we have our ion source, and we are slowly tuning it up to deliver the necessary currents for ISO DAR. Coming to the RFQ, instead of having a longer LEBT with a separate ion source, we decided to try to insert a radio frequency quadrupole into our cyclotron, and then have the ion source just sit on top of that with the LEBT contained in this six-way cross. This is a much more compact system, which is nice for underground installation. It also is a very aggressive pre-buncher. So particles coming out of this RFQ are contained within the narrow phase window that we want them to. In order to demonstrate that this can actually work, we've been awarded an MRI by NSF. And so we're currently working on mainly this project, matching the ion source to the RFQ. And this is a very old picture of the RFQ that is long outdated, but it kind of demonstrates the idea. And then we're going to build a small 1 MeV test cyclotron, a new one, to show that the particles coming out of the RFQ can be injected through the spiral inflector and accelerated to about 1 MeV per nucleon. We also will have, of course, diagnostics to understand the beam dynamics inside the cyclotron, to show that vortex motion is really something that starts to happen at these low energies, and we'll also measure the beam current and the bunch lengths, etc. One thing about RFQs is that particles coming out of the or bunches coming out of the RFQ tend to immediately start diverging in transverse directions. So we will have a quadruple singlet or a quadruple doublet right after the RFQ to refocus the beam into the spiral inflector. And we also need to make sure that the RFQ is as close as possible to the spiral inflector. So there's a little bit of a trade-off between transverse focusing and longitudinal beam growth, because the longer the beam goes without experiencing any RF acceleration, the more it will drift apart also longitudinally again. So one word about the matching of the ion source to the RFQ. This is something that our graduate student Lloyd Waits is working on. It's we are now designing a new extraction system for the ion source that will focus the beam correctly and match the beam into the RFQ. And you can see here roughly what it consists of. So here's the ion source itself. Then we have a few electrodes that start to guide and shape the beam. Then we have a massive electrostatic lens, an Einzel lens, that also doubles as a chopper. So we can focus the beam, and also at the same time we can, if we so desire, move the beam off the center and into a designated beam stop to stop the beam. This is important for machine protection, but it's also important during the commissioning of the RFQ and the cyclotron, where we want each bunch to have the full charge, but we don't want the system to be overwhelmed. So we reduce massively the duty factor of the machine by chopping it. You can see here on the right, you can see a plot that basically shows the acceptance of the RFQ in terms of the twist parameters alpha and beta. And a third parameter is, of course, the emittance that is not in this 2D plot. But you can see that that there's a wide band of acceptance for alpha and beta. And so our latest simulation, or our latest design, that also features a solenoid right before the RFQ to refocus the beam into the entrance of the RFQ, puts our beam somewhere here right into this 95% acceptance band. So that means 95% of the particles are transmitted through the RFQ and are bunched and focused correctly. For those of you who are not too familiar with RFQs, I have two slides on how they work. RFQs are radio frequency quadrupole, so that means there are four so there are four electrodes. The two opposite ones are always on the same polarity. And what that does is it creates this focusing electric field. Now they're not static, they're actually, there's an RF voltage applied to these electrodes that goes with the RF frequency, and of course there's a phase. And what that does is it continuously focuses the beam alternating in horizontal and vertical direction. If in the longitudinal direction we also add some modulations to these rods, we get a longitudinal electric field component in these along the veins, So these rods are most often called vanes. And with this longitudinal field component that of course oscillates also with the RF voltage or RF frequency, you get a bunching and acceleration effect. The RFQ is typically built up in cells, and each cell has a length of beta lambda, where beta is the velocity of the beam and lambda is the wavelength of the RF. So you get continuous focusing, you get acceleration and bunching, and this has to happen at the same frequency as the cyclotron later. And typically RFQs have a radial matching section at the beginning, then they have a long shaping section, and then they have a gentle bunching section. And after that, you can accelerate. So at the end of the gentle bunching section, you have compressed the beam longitudinally as much as possible, as much as the space charge limit lets you compress the beam. And then after that, you can actually add a longer acceleration section as well. But in our case, we don't actually want to accelerate the beam in the RFQ. We just want to use it as a buncher. So in our case, we so here's a nice little animation of a not very well matched beam, I have to say, but you can see how the beam is oscillating in X and Y alternatingly, and then also how the beam is bunched. And then here at about 1.3 meters, we have reached the end of the RFQ. And right after, you can see how immediately the beam starts diverging both transversely and longitudinally. So this just for demonstration. Our RFQ accelerates the beam from 15 keV to 70 keV. And then we inject our 70 keV beam through the spiral inflector. So our original design was done with ParmTech. Then we calculate the fields of this RFQ with an FEM method, and then we track the beam through track. Now we actually have handed this over to a company in Germany called Vortex that we subcontract for building this RFQ for us. And they have done extensive beam dynamics studies in addition to generating the technical design of the RFQ that you can see an earlier iteration of that here on the left. Here are just 2 of the 4 rods of the RFQ. Our RFQ design is going to be a so-called split-coaxial RFQ design, where the vanes or rods are not connected to the RFQ tank walls, but they're connected pairwise to the entrance and exit flanges. And this changes the eigenfrequency of the structure, the dependency of the eigenfrequency of the structure to the diameter. So typically, the lower you want your frequency to be, the larger your tank diameter has to be. In the case of the split coaxial, we can actually have a very small tank diameter at a very low frequency. As I mentioned before, our frequency is 32.8 megahertz for the cyclotron. So the RFQ has to be the same frequency. And this would be a 1.5 meter diameter or so structure normally. But with the split coaxial one, we can actually keep this below 28 centimeters, which then lets us insert it into the cyclotron yoke. The emittance growth inside the RFQ is fairly small for this design, which is what we want, of course. And the transmission rate is upwards of 95%. Another interesting aspect of this RFQ is that the power requirements are very small. Since we are not accelerating this beam to any high energy or even medium energy, we only require less than 10 kilowatts of power from our RF amplifier. So this is a nice added bonus. Coming back to this overview picture, so we've talked about the ion source, we've talked about the RFQ, and now we'll talk a little bit about the spiral inflector and the central region. And so this is one of the more tricky parts. Once we have the beam from the RFQ, which is highly divergent, we need to refocus it. And here on the left, you can see a calculation of that was done with COMSOL. Which is a multiphysics software package where beam is refocused into the spiral inflector and then guided through the spiral inflector onto the median plane. And one thing you can see is that the beam is actually growing quite a lot in the vertical direction due to energy spread inside the beam from the RFQ bunching. And then once the beam, but that is actually not a problem. We can build a cyclotron central region that accommodates this large vertical size. And it helps with space charge because the larger the beam is vertically, the less there's going to be radial and longitudinal space charge. So once the beam has gone through the spiral inflector, we have to guide it through a magnetic field. Here you can see the magnet poles for our 1 MeV test cyclotron. These black parts are actually vanadium permandur inserts that that hopefully will help increase the flutter, which is just a difference between high and low magnetic field regions, difference between high and low field in the valleys and the hills. And then in between those magnet poles, we have our RF electrodes or Ds to accelerate the particles. What we do then is we calculate the magnetic field of this of a realistic cyclotron model using an FEM software. And we calculate the RF fields from these electrodes, and we put them together, and we track this in a particle tracking code. In this case, we actually subcontracted another company called AIMA in France, and they did the first iteration design of our central region for us. So they took these particles and then they tracked them through the central region. And here in dark blue, you can see the Ds, and in green, you can see the grounded parts. And so every time, all the blue and red and the particle trajectories is actually where the particles are crossing the gaps. I mean, technically it's the phase of the particles, but it kind of guides your eye to where the particles are crossing the gaps. And so they're accelerated and go on this spiral trajectory. Now we have to clean this beam up a little bit because, as I mentioned, the energy spread out of the RFQ is quite large. And so particles, as you can see, go on various different radii trajectories here. So we would then put collimators, and these collimators help reducing the beam halo. Here you can see a probe that is inserted radially into the simulation here where this blue line is at 210 degrees. And then you can see particles crossing this probe where are registered, and we plot it as R and Z. And you can see that we can get about a 1 centimeter turn separation edge to edge between the 4th and the 5th turn, which is what we asked IMA to design this for. Now there's a lot of optimization that still needs to be done for this design. And one caveat is that this was done without space charge. So this is something that we're just now actually redoing, because we now have a new beam from the much more refined RFQ design, and so we'll redesign our central region with this in mind and with space charge effects included ab initio. And we do this by using the OPAL code. I think all of you probably know OPAL. It's a particle in cell code that is hosted at PSI and developed by many people all over the world. When I was at PSI, actually, one thing I did together with Andreas is to develop this this new model of tracking a beam through a spiral inflector field using the electrodes as boundary conditions, the realistic electrode shapes as boundary conditions for the particle termination, but also for the field solver. So that includes then mirror charge effects of the particles going through the spiral inflector. One aside is that during our tests with the earlier 1 MeV cyclotrons, we actually had a spiral inflector, and this is a model of this particular spiral inflector. We actually were able to show that 94% transmission in a large spiral inflector is achievable, which was our goal back then. And so that means we can really inject our more rigid H2 plus beam into the cyclotron and accelerate it for a few turns, as you can see here in this OPAL simulation. So this is something that that we noticed was necessary. We needed to improve existing codes, and we needed to extend what the OPAL code was able to do in order to be able to realistically simulate our beam and to show that this can actually work. All right, so talking about PSI, let's go back to Injector 2. What is the really interesting and important thing that we can learn from Injector 2? It's a similar energy as we need, and it was able to accelerate, or it is able to accelerate up to 2.7, and probably, if they stretch it a little bit, 3 milliamperes of protons. And the reason they can do that is they have very high energy gain per turn. That's very important, and we will have that too. But they also have something called vortex motion. This is something that wasn't planned for in the cyclotron. It just happened, and people started noticing it. And then a previous postdoc of our MIT group that also worked with Andreas at PSI was able to simulate this with OPAL and show really good agreement between the OPAL simulations and the measurements. And so we are now quite convinced that vortex motion can be actively used in the design and acceleration and simulation process. Just to give you an idea of what vortex motion is, if you follow the beam and then along its trajectory, then the longitudinal direction is always tangential to the beam, and the transverse is always radially outwards. Just to explain what the labels here mean. And you start with an initially mismatched beam. You can use collimators and vortex motion to scrape away some of the halo, and the beam automatically will start curling up into this round distribution. So after 40 turns, you can see that the longitudinal and the transverse beam distribution are approximately circular. And it will stay like this because the particles will shear always tangentially to the beam in the direction determined by the direction of movement of the beam in the cyclotron. So this can really help with extraction, because now we have removed any kind of halo, and the beam is not actually growing very strongly. And that means we will have good space between two adjacent turns to insert our electrostatic septum. Let me show you a video that I made of this in our ISO DAR cyclotron, or not. Let's see, let's try this again. Here we go. On the left, this is the beam without a field solver, so there's no space charge in the left one. And on the right, we have a FFT field solver in the OPAL code. This is in the isochronous magnetic field, and you can see how halo particles are starting to develop, but you can also see how they always kind of go around the beam with these wings. And after a while, you can notice that the left one always comes back to this elongated cigar-like Gaussian distribution, whereas the right one forms this circular distribution. And then if we continue tracking, this circular beam distribution will not change much anymore. And the better the beam is matched in the center of the cyclotron, the more circular it will be, and the less it will breathe in the longitudinal and horizontal direction. Now, of course, these low density halo particles are a bit of a problem. They will still activate the septum more than we want. And so these we can scrape away using collimators in the central region. Here I'm just plotting the initial beam of this simulation. And then when we track the beam through the central region all the way out, and then we use the electrostatic deflectors and magnetic channels to extract beam. And I'm showing this because I also indicated here where I put a probe that I will show on the next slide. So the probe really just registers in OPAL particles passing through this line with no vertical, so with no respect or no yeah, doesn't care about the vertical direction. So all particles passing through this line are registered. And so when you then put these collimators in these first, let's say 6 turns, before the beam has reached 2 MeV, which is important because this is kind of the threshold for when activation starts to happen. And so we want to put our collimators below that activation threshold, so that we only have to consider heating up of the elements, but not nuclear effects that lead to activation. So here's just just one example of this. We put a number of collimators, and then we look at the distribution of the beam on this probe, and you can see here the individual bunches of subsequent turns, and then you can see here also that in between the n-1 and the nth turn, we get a very low halo contribution. So this drop here is because the beam now, the cyclotron magnetic field starts to lower. Actually, we're reaching the fringe region, and here we then have. So this is binned in 0.5 millimeter bins. So that kind of gives you an indication of how much beam loss you will have on a septum that's 0.5 millimeters thick. So it's below 100 watts, which is what we wanted. And here you can also see a scatter plot of the same data with the septum indicated. Now, this is a little bit older actually. By now we have reached something like 50 watts on the septum with by carefully tuning our simulations. And we have also improved our realism quite a bit by including these septum electrodes and the puller electrodes as collimator objects in OPAL. So that means we can in 3D register how many particles are lost on the whole electrostatic on both electrostatic deflector systems, and we can calculate these fields through finite elements methods. Here's just 2 pictures. So this is what we generate in Inventor, which is CAD software. And then we export this and load it into COMSOL and generate the electrostatic field, and then load that electrostatic field into OPAL. And then OPAL uses it for particle tracking. And here you can see how the beam in the last turn is peeled off using these 2 deflector electrodes. So what you can also see is that, of course, there are several particles still striking the electrodes. This is actually wrong. Sorry, this is from a previous simulation. So right now, our current design has about 50 watts loss on the first extraction septum, and 0 watts on the second, because in the second one we already have much larger turn separation, and so we can much nicer guide the beam through this second system. And yeah, so this is how it looks like if you plot 10,000 trajectories, and this big plot here in the middle is when you plot just the centroid of the beam. Finally, the beam that comes out of this system is actually quite well behaved. It's not too big. We can still shape and guide it through an electrostatic through a magnetic channel and out of the cyclotron. One thing that I mentioned earlier on is that that there is something that we can do involving H2+, which is something that no other particle can do. Well, I mean, you could, yeah, that no other particle really can do is you can protect your septum with a very small stripper foil. So this would be a carbon foil that is placed right before the septum electrode, and so halo particles that are in between the turns would then go through this foil. The electron would be removed, and the 2 protons that are resulting will have a lower rigidity, and so they will go on a different trajectory. And we can plot this out. We can design the cyclotron such that these protons will then actually go out and be terminated in a designated beam stop, or we could even think about using them for something like isotope production or something like that. This only reduces our total beam current by a very small fraction, by about 0.02% or so. So it doesn't matter at all for the neutrino experiment, but it matters a lot for protecting the septum from these particles. All right, so in summary, I think with our design and simulations, we have shown that that 10 milliamperes of protons are possible from a compact isochronous cyclotron. We have a pretty good preliminary design for ISO DAR, and we're working on a more involved technical design now. And a large simulation effort is underway, which we're constantly updating and upgrading. And one of these upgrades that I'm going to talk about on the last few slides is actually trying to use machine learning. We're also doing a lot of prototyping. So we have built an ion source. We're now modifying it and doing systematic tests on it. And we are building an RFQ, and soon we'll build one MeV cyclotron, and then we'll put it all together to have the first ever prototype of RFQ direct injection of a 10 milliampere or 5 milliampere H2 plus beam into a compact cyclotron. So let me now switch gears a little bit and talk about machine learning. This is really something we, as a collaboration, and me personally, just recently got excited about when colleagues at PSI and SLAC were using ISO DAR, our cyclotron design, as an example for the surrogate models, which is something that I think could prove very useful. So in a surrogate model, particles. So typically, the particle accelerator simulations that we need to do in order to design our machines are quite complex, and they are very slow to execute. So this plot I took from this paper here, where also the ISO DAR example is located. And so if you want to optimize your design, that requires repeated evaluation of points in what could be a very large parameter hyperspace. So it might be that you have tens or even 100 or so input parameters that will, after the simulation is run, lead to some output parameters, right? That you want to optimize on. So in a surrogate model, you can train a neural net on a sparse set of points in this large parameter hyperspace, and then you can evaluate the surrogate model instead of your physics simulation during the optimization process. And this is depicted here in this schematic. So here's this example that I mentioned, where a neural net was trained on 2,500 points with 5 input parameters and 12 output predictions. These would be the lost particles, the energy spread, and then 3 parameters for beam size, and 3 parameters for emittance, and 3 parameters for halo. They reasonably reconstructed the Pareto front. As you can, this is just one example of the many that are in the paper. Where here you can see the in orange is what the trained neural net would predict, and then in pink you see the verified actual points from the high fidelity simulations. So they're close together, but they're not perfect. So there's definitely some room for improvement, but it's very encouraging. And you can also do some iterative retraining with subsets of the 12 output predictions. And that was also shown to improve the overall results. So with this in mind, we want, as the ISO DAR collaboration, we want to actually dive into this a little more and use surrogate models for optimization of the LEBT and the matching of the beam to the RFQ. So this would be our kind of a sandbox problem to learn the ropes. And then we also, because here we have quite decent solutions for comparison, and it's the number of parameters is a little lower, and we have a very clear goal. The next step would then be to optimize the spiral inflector and central region, and then finally the full cyclotron to optimize and to do some uncertainty quantification. And then finally, this might be a little highly aimed, but we would like to add this all together in a start-to-end model, kind of a virtual accelerator, as also Jean-Luc proposed in the letter of interest for SNOMAS. For help during commissioning and tuning at runtime. And one, I think, nice thing about this would be that we could then do like actual measurements, and we could feed these these data points back, the ones that we get from the experiment, back into the models, and we can refine the models and retrain them. We also have kind of this progression from a small problem where we just use the ion source and the LEBT, then use the full RFQ dip, which is RFQ plus 1 MeV cyclotron, and then use the full ISO DAR cyclotron. And we gain understanding all the way. And there's a lot to be learned from that, I think. And there's a lot that we need to learn. We need to understand what the uncertainty of these machine learning based modeling principles are, how scalable they are, and what the physics, so how we can use physics to improve these models or to reduce the complexity of these models. All right, so that brings me to the summary slide. We're pushing the intensity frontier through cost-effective compact accelerators. We developed some code, which also helps us to understand high intensity. It has a lot of impact on other fields, medical isotopes, energy, particle physics, neutron sources, and I'm happy to show you a couple backup slides on that if you're interested. And we're building actual machines, but they're small enough to be at the university level, which I think is really something very nice that might be underestimated sometimes. Is it gives us the opportunity for teaching students on actual hardware. So that's the hands-on teaching here that I like to emphasize also. All right, and with this, I would like to thank you, and also all of the members of the IsoDAR and Daedalus collaboration, especially the members that are contributing to the accelerator design. I'm not going to list them all. Thank you. And of course, NSF, where our money comes from. And thanks for the attention.
Yeah, thanks a lot. Yes. Very nice talk, Daniel. So let me first stop recording as promised here, so to get a little bit